let me just make a very quick introduction that has been already made yesterday, but it's a pleasure to have Mauricio Romo, that he's going to give us the second lecture on supersymmetric localization in 2 dimensions and applications. Mauricio is an expert in this subject, and so he's affiliated in the Shanghai Institute of Mathematical Science and Interdisciplinary and interdisciplinary sciences and Fudan University. And yeah, so it's a pleasure that Mauricio is talking to us. You
Oh,
can
thanks a lot, Nana, for such a nice introduction. Um, okay, so I will continue with where we more or less where we finished yesterday. So yesterday we just give some introduction to these gauge linear sigma models, very basic one. So I will start with just clarifying or remind you a little bit of the example. First of all, so the example we did to illustrate how sigma models are, gauge linear sigma models are related to geometry. I remind you, we'll flash it on the screen. The example was this abelian gauge theory in 2 dimensions, where the representations and everything was set such that the two R symmetries that we discussed in detail last time, the two R symmetries are unbroken. So there's no anomalies. They are non-anomalous. So, right. So I will remind you, I will say a few more details on this example. So the example, the equations, the classical, the classical, the classical vacuum equations. If you remember, indicates that phi has to be in this space on the critical points of W intersect with the zeros, sorry, this need to the -1 of set. So this was the moment map. Or if you want, so these equations for the case at hand, critical type of W, were given by this in this example, dfm dxi equal to df equals fm equals to 0. Here is at p. So and here I goes to n. And the moment map equations in our example, again, these equations were given by minus p norm of p squared plus sum I equal 1 to n of xi squared equals to this theta, which was just a real number. So as I mentioned, the equations for sigma, because someone asked, the equations for sigma that we wrote the last time, in the non-abelian case, there was of this form. In the abelian case, you only have these 2 here, where the action of sigma on phi, well, in this case, because it's abelian, this is U1, this equation, the commutator is not there, it's automatically 0. And the other is just the product of sigma and sigma bar. So what these equations are saying, just because someone asked last time, these equations are saying that sigma belong to the Cartan subalgebra of the stabilizer subgroup of point phi belonging to of phi classical. So meaning you just pick a point here in this space, and then you check what the stabilizer, meaning the subgroup of the gauge group that leave it invariant, and then sigma belongs to the Cartan subalgebra of that subgroup. So in the case at hand, if zeta is larger than 0, you can prove that the stabilizer is trivial. Hence, sigma is identically 0. right? The Cartan subalgebra of a trivial Lie group is 0. And if zeta is negative, the stabilizer is set n, set sub n. Actually, set sub n plus 1. So, sorry, set n. Set n, yes, set n. So that means it's a finite subgroup. So set n inside U1, right? So it's a finite subgroup, therefore the Lie algebra of a finite subgroup is also 0. So also symmetrically 0. This is not going to happen in general. In non-abelian theories, this usually doesn't happen. Then this analysis is not enough to determine the infrared dynamics of this model. So if you do full, more complete detailed analysis of the IR dynamics, so the complete, we can say the complete IR dynamics of this model. If you study the complete IR dynamics, you will find that we can write as a cylinder. This is a very old result by Witten. You can write as a cylinder, so this direction is theta, this direction is theta. I remind you that my convention was theta minus I theta for this Fi theta parameter. And then around this region here, where theta is positive, around the IR dynamics are described by a sigma model with a curved target space with target X, which is the Fn equal to 0 inside Pn minus 1. And if you study, so this is not very hard to see because last time I gave you as an exercise to show that actually the critical points for zeta positive indeed corresponds to this variety. So it's not hard to imagine. Of course, there is more analysis. You have to do the analysis of the expansion of the potential around the critical points. And what you find is that the normal direction to this variety are massive. Therefore, what you get is a sigma model with this target space, and all the coordinate, the massless fields are tangent directions. So here massless fields are tangent directions. You have to, of course, have a more complete analysis for that. And if you go to this, let's say this area of the cylinder, you get that your IR dynamics is described by Landau-Ginzburg. So this is Landau-Ginzburg. That's very beautiful. So Landau-Ginzburg orbifold. That's a deviation where the fields X belong to the n mod set n. Okay, that's the target space. So this is like a sigma model with this target space, but because the target space is non-compact, you are allowed to have a potential. And in this case, the potential of the sigma model, I will denote with LG, is simply this polynomial, remember, of homogeneous of TUN. So these two theories are they have completely unbroken 2,2 supersymmetric as I described the last time. And both theories, if you keep flowing to the infrared, both of these theories are characterized, as you may know, as these are SDFTs. So they actually, the 2,2 supersymmetry get enhanced superconformal symmetry in the infrared fixed point of these theories. That's also another conjecture in physics. And the way to see it, if you study these theories separately, in this case, is because of the quasi-homogeneity of F, and in this case, it's because this X is a Calabi-Yau manifold. Okay. So this is an example of a GLSM, very simple one. And here is the relation. You see there is a relation with geometry, with X, and also there is a relation with these Landau-Ginzburg models. So how are they related? I just showed you, right? The way they are related is by the formation of the phi theta parameter, which in the infrared, it becomes a marginal coupling. There is one more thing to say about this theory, maybe that kind of may become important later, which is this theory also has, there exist values of T such that the theory becomes ill-defined. So there is a singularity in this space. In this cylinder, there is also singularity. This also was analyzed by Witten many years ago, more than 30 years ago now. And the way to do it is by looking at analyzing what you have to do is analyze the something called the effective twisted potential. That means the region where the VEV of sigma is very large. In that region, as I showed you before on the Lagrangians, sigma, the wave of sigma acts as a mass for the chirals. So in that region, you can integrate all the chirals, and therefore there is an effective potential for sigma. That's what's called the twisted. This is what is called the effective twisted potential, because sigma is a twisted chiral field. And critical points can be obtained by studying critical points. So critical points, or sorry, no, I shouldn't call it singular. I should call it singular points or singular points. Singular points are given by this potential is logarithmic. So the correct way to write the equation is like this. So critical points of the effective twisted potential gives you the singular points. So in this example, we're going maybe to talk again about the twisted potentials. I'm not going to write it explicitly, but you can compute it. And in this example, the critical point is going to give you a point here, which I can tell you specifically that this point is T equal n log of minus n. Okay. Very good. So that's about gauge linear sigma models in general. That concludes. So today, now we are going to talk a little bit about philosophy or general ideas of supersymmetric localization, or precisely of this class of models. And I think everything must have happened. And I hope I can give you at least the essential idea clearly. So, of course, I cannot do this. I cannot describe in complete detail this computation because it's super long. But the main idea I want to remind you is, so we are going to give a sketch of the idea behind, and also why you will care about something like this. And later I will specifically talk about the one that the localization that appears on my work, which is we will focus on the case of the Riemann surface, the world sheet being a disk. A disk is a disk, so the boundary of the disk is just a circle. So this is an interesting case because the localization computation actually is not so hard, but there's a lot of subtleties regarding the fact that we have boundaries. That sometimes in QFT, one doesn't learn very basic things about theories with boundaries, so maybe it can be helpful for you, even if you are not doing supersymmetric localization. So let me say first what's the idea behind why we would like to do this thing. So before recall we have two nilpotent charges, which we call QA and QB, and also their conjugate. So these are nilpotent charges. And when you have nilpotent charges, you can define a subsector of the theory of your theory given by the cohomology of Q of QA slash QB, we are going to say. So this is something that you may be familiar if you have done, for example, BRST, gauge fixing techniques and things like that. Every time you have a symmetry of the theory, these Qs, remember, they are symmetries of the theory, completely non-anomalous. If you have symmetries of the theory that are nilpotent, you can always define a subsector of the cohomology of this charge. And the reason that the cohomology makes sense is because QA or the exact operators or quantum field operators have identically zero bets. We are going to get, or no, not only bets, identically zero correlators. We are going to talk. I'm going to say a few more words about that. Because they are unbroken symmetries. If you put any QA exact operator and other elements of the cohomology in a correlator, you are going to get identically zero result. So that's why the cohomology of this nilpotent operator define a subsector that you can study separately from all the other sectors of your theory that are certainly going to be much more complicated. Now, the problem with these operators and these symmetries is the following. The problem, let's say, if you want to study this subring of operators, subset of operators on theories on curved worldsheet, you find a problem. Why? So supersymmetric transformations has acting on fields take the form delta supersymmetric. It will take the form of the following form. Something of this form. So here, these Q are the supercharges that defined the previous lecture. So you can put here some epsilon plus and minus. This epsilon plus and minus are the parameters of the supersymmetry, okay? So in general, in a general worldsheet, I will call it worldsheet, you can call it spacetime if you want, sigma, epsilon plus minus, and also the bar. Remember that the bar is just a name, nothing to do with conjugation, are sections of S plus minus, which are the spin bundles given by, in this case, S plus is given by, let me see, S plus is given by the canonical bundle of sigma, and you take the negative root, or if you want, you can write it the conjugate of the canonical bundle. This is the canonical bundle. And you take just the square root. And S minus, this is a definition if you want, is the canonical bundle of sigma, and you take a square root. Okay? If you are more familiar with the physics, this is just left and right while fermions, left and right while spinors. Okay, it's just that. But if you are more fancy, if you call that's on flat space, but if you are in a course worksheet, the correct way to talk about this is sections of the spin bundles.
Mauricio, I have a question.
Yes, please.
When you mentioned that the cohomology is given by these charges, so these charges can be seen as differential forms or elements of a certain type of cohomology, or what type of cohomology is this one?
Good. Yeah, so I was trying to be vague about that because this is kind of a general physics. In the physics spirit, this is general. Like, it's true that in the case of sigma models, for example, this QA and QB can be identified with the RAM operator or Hoche the RAM operators, differential operators acting on forms. That's and the cohomology becomes a cohomology that you learn like in differential geometry.
Okay, so it's like the RAM cohomology.
Exactly, in that example, like if you have a sigma model. But if you have like in a general field theory, in a general supersymmetric field theory, or even in a general field theory, if you have an nilpotent operator, you can define a subsector. An example is when you learn about BRST. BRST, when you do gauge fixing in, let's say, QED, and you learn about the BRST technique. So there, what you do is you construct an nilpotent symmetry of your theory. But there's no supersymmetry, nothing like that. So a priori, that nilpotent symmetry doesn't have any geometric interpretation. But you still can define a subsector, which is the Q cohomology, meaning Q cohomology in the sense in the sense that I look for physical operators that are in the kernel of Q divided by operators in the image of Q. So operators that are Q acting on something. Abstractly, I can always define that, right?
Yes.
In a physical theory. So what I'm saying is nice properties that these operators have always nice properties, regardless if we can interpret it geometrically or not.
Okay, thank you.
Okay, no problem. So if you want to study such a sector, you need to have unbroken supersymmetries, of course, unbroken supercharges. At least some of them. So if you go back to the origins of this supersymmetry, you have that, as I was mentioned, the general supersymmetry transformation acting on fields take this form, and these epsilons are the parameters, if you want, the parameters of the supersymmetry. So as we vary the Lagrangian, you get delta L equals something like that. You will have that delta L. You can show that it's like this, something like this. It takes this form. I'm not going to write what is G. But whatever is G, this G mu, is the supercurrent. Le Lagrange, so assuming epsilon plus minus and the bar depends on coordinates, you are going to get something of this form, epsilon bar minus G r. Something like this, plus maybe boundary terms. So this is what you want. So we're not going to worry much about the boundary terms right now. But let's say you are in a manifold on sigma with all boundaries, you have this type of, but the variation of the Lagrangian gives you something like this. So all these G are super covariant. So how do what we want is it's zero, right? That this is a symmetry of your action. It's a symmetry of the action. So zero may be up to boundary term zero, boundary term zero. Sigma has no bound for it to make it simple. Later we are going to the case with bound, but let's say sigma has no bound. Then this is what you want to happen, right? That this is zero. So how you make this zero? That implies if you want to make it zero, let's say I'm optimistic, I want to preserve all the supersymmetry because those were my assumptions. Then you need that this is zero, right? This is covariant derivative, right? It's covariant because it's not an scalar. Epsilons are not scalar. Even on flat space, you know they are not scalar. So this covariant derivative acting on this is equal to zero. So that means, but in sigma not flat, there doesn't exist constant sections of the Pinot band. Okay, what this means? Again, this means that if you work on a manifold that's not, in the case of flat space, what you do is you say, oh, the epsilons are constant, and then everything works, right? What I wrote there is identically, all this is identically zero. But the problem is in a curved manifold, you cannot do that. If you impose that the spinors or these parameters are covariantly constant, you are going to find that the only solution is that the epsilon is zero. Okay?
Can I ask you a short question about this last statement?
Yes, yes.
Is this a question about the geometry, meaning flatness, or about the topology of the spin bundle?
Actually, yeah, I was also a bit loose. It's about the topology. So in let's say in a torus, it's okay. In a torus, it's okay. On R2, it will be okay.
Is this just a question about the triviality of the spin bundle, or if it's non-trivial, it has no constant sections? Is this the
That's
statement?
right. That's another way to say it. If it's trivial, it will have constant sections, obviously. If it's non-trivial, well, it may be, but in this case, no, it doesn't have. No, it doesn't have yes. Because if sigma is curved, let's say sigma is genus zero or genus 2 or higher, the spin bundle is not trivial, and then you have actually you cannot have constant sections. In the sphere, you cannot have constant sections. Okay.
Thank you.
Yeah, no problem. So if you want to do this in any worksheet, if you have to compute your cohomology in any worksheet, you have to do something about that. So that means we cannot define a cohomology of Q in a Q meaning QA, QB, or in an arbitrary worksheet. Okay. So that depends if you want to do it. Maybe you don't. But
sorry,
general,
Mauricio,
yes.
I lost you in the last bit. What is the argument to say that you can't define a cohomology?
Because you cannot define Q. Because you cannot define Q. Because remember that
because
Q
you don't have a well-defined symmetry transformation.
Exactly.
Okay.
I mean, I can define the transformation, but it won't be
But it won't be
asymmetric.
asymmetric.
Exactly. Yeah.
Okay.
So
Thanks.
the condition to the asymmetry is kind of in general, yes. So exactly, you cannot define a cohomology in an arbitrary worksheet, because I will repeat it. So you cannot define Q itself. Q itself. That's the issue, that you cannot define Q. So there is two ways around that are actually related. So there's two ways around. Two ways around are related, but they are not equivalent. I will explain this a little bit now. So one way around is something that comes from the 80s. Okay, so is perform a topological twist. So in the case, if you perform a topological twist, that means very roughly, like if I write it very fast, it's like I write the group of Lorentz rotation. I declare the group of Lorentz rotation that I call it G prime, which is to be U1 prime. In this case, the group of Lorentz rotation is just a U1. That embeds into U1R. This is R symmetry with the usual, this U1L Lorentz. This is usual Lorentz group. This is Witten's idea. Witten's from the 89, 88. So in other words, we can choose U prime U such that the bundles where E plus, E minus, etc. belong become trivial, right? Because we are changing the the worksheet, the bundle over the worksheet. We are mixing the structure group of the worksheet tangent bundle with the R symmetry. And because the epsilons have non-trivial R symmetry, you can make them actually to become element sections of a trivial bundle. Then you can solve this. You can, the punchline from those papers of 80 is you cannot do it for all the epsilons. You can only do it for two, basically. Or yes, so you can do like this, for example, or you can take like this option. So they are sections. This means sections of O epsilon. This is the trivial bundle. This is what's known as the A twist, because this will make QA well defined in every worksheet, and this is called the B twist. This is one option. This is one thing you can do. That means,
Mauricio,
yes.
sorry. I got a little bit lost in this construction. Why is it that you are saying that originally the Lorentz group it's a U1, and now you embed a different U1 on this U1 times U1. Why can you now trivialize your bundle?
Oh, it's just because now you just, okay. This a bit, I wrote it like kind of in the same way that Witten wrote it. I mean, there is a more maybe intuitive way of saying it, which is what I'm going to say next. But what you do essentially is you just declare that the Lorentz group of your theory is different. It's a different U1, not the usual U1. In other words, what you are doing when you do this A or B twist, you are literally changing your theory.
Okay.
This is a different theory from the original. The topologically twisted theory is not the same theory you started with.
Okay.
So you can, in other words, I could have told you, okay, well, if you don't like the epsilons being on the spin bundle, well, just declare that they are not on the spin bundle. But of course, this has to be consistently done, right? You cannot just change the bundles and have Yeah, exactly. So in order to have a theory that at least is related in some clear way with the theory you started with, you have to do it like this. This is kind of the way to do it.
Okay, thanks.
Yes, okay, no problem. So this is one way around. There is another way around, which is what kind of will concern us on probably a little bit the rest of this lecture and the next, which is the case you can do something else. You can say, okay, I don't want to really change the bundles, but I want to change the simplest way of putting this in a short way is change the theory such that the condition mu epsilon equal to 0 changes. So that means I deform L, the Lagrangian, to how to get this, So this is very vague. And of course you can imagine, okay, well, they have tons of ways of deforming the Lagrangian, but indeed it's very restricted. It's very restricted. So in this story, the way to do it consistently, the way to do it is by coupling the 2,2 theory, to a supergravity vacuum. That's a way to say it. So in order for this deformation to be consistent, you have to couple the theory to some the couplings that you add, the deformation that you add, have to come essentially from 2D supergravity after you froze the metric to a particular one, for example. The idea of this idea was originally studied by Vasily Pestun, but later on it was studied by many other people. I mean, many other localization results, but it was ultimately for 2D, let's say for the 2D case, it was Closet and Cremonesi that did it for the 2D case. But there's many other works. This is just the 2D case. There's many other works for other dimensions. So the original work of Pestun, where they is originally there, is for the 4D case. 4D case is a 4D n equal to theory on the sphere. Okay, so in this case, I will just give you the punchline. What you can do is that indeed, we can obtain the condition. We can deform the condition to this, something of this form. This is a gamma matrix, gamma mu, and this is Dirac over it. There are many ways of writing this condition, but this one is what is known as conformal Hillen equation, or that means epsilon is a conformal Killing spin. This S means spin. Okay, so that's the idea, but I can give you more details if you want how you get this, but let me give you the punchline now. So if you do that, there is a problem. There is another problem, however, is a happy situation, but not so happy. However, such equation can only such equation has non-trivial solutions non-trivial solutions in the cases where sigma has isometry. So let me tell you the cases you can do. So in other words, when sigma has no boundaries, the only cases where you can solve this equation non-trivially is in S2 or the torus that we said, okay, the torus is not that exciting because it's flat space again. So in these two cases, you have 4 conformal Killing spinors. And in the case that sigma has boundaries, you can have this is the disk or the cylinder. So in such a case, you have 2 conformal Killing spinors. Okay. So
I have a question. So this can only be done for this kind of geometries, or can one generalize for compact geometries or for a certain
very
dimension?
good. Yeah, very good question. So that means the point 2 can only be done for this geometry. Only for the geometries I wrote here. Only this one. Yeah,
Is
it's a
there a
little bit.
reason why, or is there like a way to know why only in these geometries?
The reason is because, okay, in this geometry, I mean, in any geometry, in principle, you can get these conformal Killing spinor equations. In any geometry, I can deform the theory to have this equation I wrote here, okay? But the problem for the arbitrary geometry is that this equation will have also no non-trivial solution. So the problem is to find the same that the other equation, right? If epsilon is covariantly constant, you can get that for any geometry, but you are only going to find non-trivial solutions for flat geometry, right? And in the case that epsilon, then I said, okay, I changed my theory, I deform the Lagrangian, and I get, and I change my equation to this. You may have the hope that you can solve this equation in more geometries, but you can only solve this equation in these 4 geometries, let's say. So it's not that such a happy situation.
Okay.
Okay. So now, just as a remark, the remark is that these points 1 and 2 can be understood as coupling the theory with supergravity backgrounds. Remember, in both cases, 1 and 2, you are changing the theory essentially, okay? If you start with the theory with the Lagrangians in flat space I wrote at the very beginning of lecture 1, or I described them. In both cases, either if you are changing bundles or if you are deforming your Lagrangian, well, you are changing the theory in some way.
Mauricio,
yes.
sorry. Yeah, I have a question about the S2, because in the S2 case, the conformal Killing spinor is not Majorana. And the superchargers don't close on the isometries. What do you do in that case specifically?
In the S2, well, okay, maybe this was not, maybe this was a bit sloppy, but since you are asking all this detail, this is all these statements, 1 and 2, are essentially on Euclidean worksheets.
Okay.
So then I think you don't have that problem.
I am not sure if
sorry.
I am not sure if the problem is solved about the Majorana condition.
But what okay, so let's say in Euclidean you can have you don't, but why do you want the Majorana condition?
so that the supercharges close on the isometries? Because in the sphere, usually what happens is that the commutator of the supercharges close on the conformal killing vectors.
The commutator and the conformal killing vectors.
So
Yes.
you don't have supergravity in the sphere or in any dimension, in principle. You probably have if you add conformal symmetry additionally.
You can have some minimally coupled supergravity, I think, in these cases, like in the sphere. But I have to admit I'm not an expert. So how this is derived direct from the supergravity background prescription.
Okay.
The people that did that, like with all gory details, is this paper. I can only tell you for sure that if you consider the sphere, if you put the field theory on the sphere, no gravity, you can deform the theory such that the parameters of the supersymmetry have to satisfy this equation. Now you have to, of course, be careful what you call the symmetries of your theory. That's true, because now if you said, okay, I want to forget about gravity and I just want to consider the theory on the sphere, well, then what I said at the beginning about all this Lorentz group on flat space doesn't really hold, right? Because I'm not in flat space, I'm on the sphere. So what you have to do is to mix, is to try to generalize what you have to do in this case. So for example, in this case, in the case of S2, what you have to do is to consider a supersymmetric extension of the isometry group of S2. So you have to, in other words, okay, maybe that was something that that I can tell you since you seem to be more familiar with this. In this case, you deform the Lagrangian, but of course, you also have to deform the algebra.
Ah, okay.
You also have to deform the algebra. Exactly. You need to, as I said, you cannot in S2, I cannot just say like at the beginning, okay, I have translation, time, or space, time translations, and Lorentz rotation, etc. I mean, because now I have to worry about global issues. So what I have to do is to think how I extend supersymmetrically the isometries of the sphere, right?
So you don't have anymore the SO3, you have another thing. SOT bar something or something like that.
Well, you have the SO3, but I have to add also the R symmetries and the supercharges in some consistent way.
Okay.
And you see, yeah, exactly. So yeah, that's a very subtle, a very technical point. It's a very good question, but yeah, indeed, that's the thing. Yeah,
Okay.
you have to take it with a grain of salt.
Okay,
And I know you can do it by coupling to supergravity, but I have to admit I'm not an expert on that. For that, if you know better, I recommend you to look at the paper of Closet and Cremonese. I just know everything is consistent inside the non-gravity, in the theory that have no gravity.
Oh, okay. Okay, thank you.
Okay. But only with the supergravity, only if you understand the supergravity coupling is how you can really see that this is essentially the only option, like the only generalization. You can say, okay, why I cannot have a more crazy equation for epsilon that guarantees me that I have a symmetry.
Yeah,
And
so you fix the problem with the R symmetry, basically, right? So,
that's right. That's right.
Okay, thank you.
No problem. No, yeah, that's a very good question, actually. Okay, so we are we're a little bit over the time for the question. So let me just to finish. this today is that to mention two things. So we are going to focus on let's say prescription. So what is going to happen is that in this case, epsilon plus and minus, maybe with the bar here, are non-constant sections. So now they are going to depend of the coordinate of the worksheet. So if we consider the theory on S2, for example, on S2 we get that if you have the sphere, there is two possibilities. As I said, there is two possibilities, or essentially, what are the possibilities? Once I have the four conformal Killing spinors, I have to tell you how I assign such conformal Killing spinors to the epsilons, right? So I have here four epsilons, and each of them can be a conformal Killing spinor. So depending how I assign the solutions to them, actually can have different situations. And they're essentially at the end two different situations. One that I'm going to call I type, and one that I'm going to call B type. So in the A type case, meaning I declare that the epsilons satisfy this equation, or I make the epsilon satisfy this equation, so they are ordered this way. Saying that they satisfy this equation is completely equivalent to say that this R is the radius of S2. So there is implicitly a choice of metric. So if you make the epsilon satisfy this equation, which is, again, it's an equivalent way of saying which conformal Killing spinor I assign to each epsilon, then what I get is that in the extremals here, I get I get something like this is something like no, I think I say the other way around. No. This is correct. Here I get something. The charge is the Q goes like QA, but near the other pole the Q goes like QA dagger. And in the other case, here we go like QB, and here it goes like QB dagger. And the equations here are if I declare the following. So if I mix them in this way, actually I should just the equation looks more like this. There's no gamma 3 here. Yeah. So this is the type of supersymmetries you can keep when you have a curved manifold. And in the case of the disk, so again, I will repeat you before I finish, just the last time. So in the case of the sphere, and in the case, or only on the case of the sphere, torus, or disk and cylinder, you can have these two options. Either you make the epsilons satisfy this equation, and you get this kind of theory where you have a mixture between QA and Q dagger, or QB and QB dagger, or you can have the option of the topological twist. So just to make it clear, so here I will put, for contrast, the topological twist. You will have like on the sphere, you will have like everywhere is just QA or QA dagger. If it's QA dagger, it's what you call the conjugate twist. Or in the case of B, you can have everywhere to be, so it's a scalar. Or here QB, you can have QB is scalar. Or QB dagger. everywhere. So everywhere here there is like A twist. A twist. Everywhere is A, and here everywhere is B twist. So only in this geometries you can have these two options, and of course these partition functions in these two cases they are different here. And okay, next time I'm going to talk more about these partition functions, and then we are going to talk about the applications. Like what you can use this result for, what the interpretation of this is of these partition functions on these backgrounds. Okay, that I finish for today.
Thank you very much, Mauricio. Yeah, for the very nice lecture that people were already asking. So as we are over time, maybe we have time for one or two questions. Even so, you had already many.
Okay, yeah, no problem.
Is there any questions?
Well, I can ask one about the twisting procedure. When you're twisting the algebra like this, what you get is a cohomological theory, or the theory is not topological?
Ah, very good question. You mean with in the prescription 2?
Yeah.
Yeah, in the prescription 2, no, you don't get such a nice cohomological field theory structure because it only works for these geometries, right? So if I want to do something like genus 2 by gluing a pair of pants or stuff like that, no, you cannot. At most you can take a disk here and glue it to make the sphere, and that's it. So you don't you don't get such a theory, but you get what I'm going to show you the next lecture is that indeed these partition functions, this one, and also the disk, indeed they have a very interesting interpretation. So,
Okay.
but no, you don't have the topological field theory structure. That's only that to get that only on this prescription 1.
Okay, thank you.
So I have a short question. So when people do this localization computation, for example, for mirror symmetry, to shaking that on the sphere, so you say that these are different partition functions, that this is like a different theory. So what ensures you that what you are getting there, it applies for the standard GLSM with the mirror prescription if you are doing the computation in S2?
So there are two things there. One is about mirrors of the theory, and the other is about this prescription to the computation. So you have to be, in principle, very careful there indeed. You have to, if you do one of the computation, either of them, like the sphere with the A bar, or the sphere with the A twist. I mean, these are well known now, but at that time it was not that clear at the beginning. But if you do this prescription, and you can say, okay, if my theory is a conformal field theory, I have a mirror. And I should be able to do exactly the same. I mean, because mirror theories are equivalent. So whatever I do on my theory here, I can do on the mirror. The non-trivial question is how I match. So you have to, for that, you have to look at the symmetry algebra and say, okay, how we transform under the mirror, and then ask yourself which operators then map to the mirror. So, for example, in the A-B twist, we know when we have mirror symmetries, each side of the mirror you can do A twist and B twist for a CFT. But it's not the A equal to A that we know. So you have to see, okay, if I do A twist, then under the mirror isomorphism of the algebra, I can see how QQ bar are exchanged. So I know QA, what I call QA, is exchanged by QB. So, okay, that gives me the first intuition that if I compute something on the B-twisted theory here, I should match with the A-twisted on the mirror side and the other way around. I don't know if that answers your question. But...
Okay. Yeah. No, I think, yeah. So I think this is useful, but yeah. So it's in a way that you can only do the localization computation in S2. So what you are really computing is a different partition function, no? So not
That's
the
correct. That's correct.
so.
It's not because usually you will write like the flat space, let's say the flat space action define my theory. And then if I put on a curved manifold, what you do is you just covariantize everything. Okay. That will be the natural theory on a curved manifold. But the ones that you obtain from this supergravity background coupling, etc., no, they are not just covariantizing. They have extra couplings that involve the curvature, for example, that you will not see just by covariantizing.
But still, even so, it's a different theory. It's a shake, no? That you can match the mirror to
Yeah. Because whatever is my modified theory still, I can say, okay, I still started from an SCFT and I modify it. So I can say, okay, when I was on an SCFT, I have a mirror, so I expect that the modification also can be done on the mirror and I can match. But it's true that it is a bit of a leap of faith.
Okay.
It's not like entirely clear, yes. But it works. I mean, in examples, it works. So.
Okay. Thank you, Mauricio. So, okay, so let's thank Mauricio again. We see the third lecture tomorrow. And